Assalamu alaikum. Welcome back. We are now at lecture 5 of our fine-tuning of the universe series and still exploring the initial conditions of the Big Bang. This is actually lecture 3 in that sub-portion. And so far we have seen the really amazing and mind-boggling precision that the Big Bang needed to have in terms of things like matter, energy, density, expansion, speed, etc., to allow even a remote possibility of life. But that's not all the Big Bang needed to have. There were other initial conditions that we may not think of that needed to be satisfied. And to make the lectures a little bit more exciting, I have brought with me a visual aid. Here it is. I think you can tell what this is. This is a golf ball, and a golf ball has dimples. It is spherical, but it is not smooth. It's a little bit rough with little dimples throughout. Now, it turns out that one of the necessary initial conditions, in fact, a very stringent initial condition for the Big Bang, is that it needed to be smooth. So you know that the pits on the golf ball are very small. It's not terribly rough, but it turns out that the Big Bang needs to be incredibly smooth. What does that mean? Well, again, I've pulled something from John Leslie's Prerequisites of Life, and he himself is quoting well-known scientists like Paul Davies. But the idea is, you know that the universe is expanding since the time of the Big Bang. Now, imagine rewinding, going to the outer reaches of the universe and rewinding it back in time to the beginning, right to the Big Bang. And when you mathematically work out this rewind, most of the time, you're not going to get, at infinitesimal sizes, you're not going to get a perfectly smooth sphere. You will get what is known as a chaotic or ragged Big Bang. Things that are at slightly different distances, all moving together at the same speed. Think of it as a little ball with maybe some spikes. And it turns out that if the Big Bang started off in a chaotic or ragged way, then it would have really been impossible for any life as we know it to evolve. Why? Because the chaos of such a Big Bang, it is said, could evolve toward cosmic smoothness only at the price of producing a great deal of heat. The interaction of the rough portions together would be problematic, because the idea is that the different portions of the Big Bang are expanding at such a rate that they do not communicate with each other. They are expanding initially faster than light can travel across them. And so their movements are not coordinated. So imagine a crowd of people moving smoothly outward from the center. They have a plan of how to move, and they will gently and smoothly disperse. But imagine a crowd of people right at the center where it is very dense, and they are trying to, say, run away from, you hear of all of these incidents in, say, a nightclub or something where a fire starts and people are all trying to get out, and they then end up trampling each other. Why? Because they're not moving in a coordinated way, and so they bump and jostle each other. And in a chaotic Big Bang, the different bits and pieces that have not had time to communicate together, to coordinate their movements, would end up jostling each other, and that friction would produce life-excluding temperatures or possibly black holes as they bump into each other and aggregate. And this in cosmology is actually known as the Smoothness Problem. And the famous physicist Paul Davies wrote that frictional smoothing away of even a tiny amount of early roughness would, quote, increase the primeval heat billions of times. And that would actually be disastrous. And if the primeval material was churned about at random, it would have been overwhelmingly more probable for it to have produced black holes than stars. And that the odds against a starry cosmos, according to his calculations, would become 1 followed by 1,000 billion zeros at least. This quote is found in his book, Other Worlds. And here again, just to kind of cut through all the fluff, the smoothness problem says that unless the Big Bang is incredibly smooth, the odds against the initial conditions being suitable for star formation are 1 followed by 1,000 billion zeros at least. And so one of the very stringent initial conditions on the Big Bang is that it had to be incredibly smooth, and we have no idea why it started off so smooth. Because if we rewind the cosmos now, we would actually expect it to be ragged or rough or chaotic and not smooth. And so this is, again, another amazing instance of fine-tuning. Now, I brought with me another visual aid. Give me 1 second. Here it is. Now, you can see this. It is a ping pong ball. A ping pong ball is perfectly smooth. Now, imagine if the Big Bang were perfectly smooth. We know it had to be extremely smooth, but imagine if it were perfectly smooth. What would happen? Well, if it were perfectly smooth, it would, sorry, the ping pong ball keeps trying to slide off the table here because it's so smooth. The golf ball just sits there. If the Big Bang were perfectly smooth and everything were expanding out, there would be no center for things to condense into stars. So what we actually need is something that is extremely smooth, but with just a little bit of lumpiness. And those lumps are a little bit denser than the rest, so they expand a little bit slower. And when they expand a little bit slower, then their gravitational pull is a little bit stronger than other areas that are expanding faster because the matter is not becoming so dispersed. And that stronger gravitational pull now pulls more matter to it and expands even slower, and it becomes a self-perpetuating thing. And those little seeds of inhomogeneity, or those little seeds of tiny, tiny, tiny roughness in a smooth Big Bang, become the seeds of star and galaxy formation. And so the Big Bang has to be very smooth, but not perfectly smooth. And the lumpiness quotient has actually been calculated. I think we've mentioned Martin Rees before, professor of astronomy at Cambridge and head of the Cambridge Observatories and Astronomer Royal of the United Kingdom. And his calculation is that the lumpiness quotient, which he calls Q in his book, Just 6 Numbers, and that is a book about fine-tuning, very interesting book if you're interested in this topic, has to be about 1 in 100,000. And so he says that the formation of galaxies, clusters, and superclusters obviously requires the universe to contain enough dark matter and enough atoms. We'll get to the dark matter in a minute. But we've seen that something else is needed as well, namely initial irregularities to seed the growth of structure. The number Q measures the amplitude of these irregularities or ripples. Why Q is about 10 to the minus fifth is still a mystery, but its value is crucial. If the irregularities were too big, then it would have been like a golf ball, and we've already seen that that would have been disastrous. If the irregularities were too small and the Big Bang was perfectly smooth like a ping pong ball, that would likewise be disastrous, and no stars or galaxies could have formed. And so we need the right lumpiness. And here's a simulation that I pulled off the web about how the universe sort of evolves and the lumpy portions, which are the dark clusters, get bigger and bigger, and they become the seeds for stars and galaxies. And so that lumpiness had to be precisely fine-tuned. Now, it turns out that the smoothness and the lumpiness are not quite enough, that something else was needed. And that something else, to pull the matter together into stars and galaxies with a Q or lumpiness quotient of 1 in 100,000, is dark matter. And this is what I'm calling here the startling discovery, that when scientists attempted to weigh the universe, they made an amazing discovery. You and I, and everything we know, all of the stars we see, all of the interstellar gas, is made of ordinary matter. Matter that is made up of neutrons, protons, and electrons. But it turns out that between all of the ordinary matter, and in fact, vastly outweighing all the ordinary matter, is something entirely unknown to us, and that is dark matter. And it's called dark matter because we have no idea what it is. It's an invisible form of matter. It does not react to light, with light, and it's known to us only because of its gravitational effects. And dark matter has been known for, I would say, roughly about 50 years or so. And it has been a holy grail or quest to discover the identity or nature of this dark matter. Why scientists believe dark matter exists is a very, very fascinating story. There are multiple lines of evidence that are very, very strongly suggestive that it exists. And the quest for the identity of dark matter is one of the great quests of particle physics, but they take us far afield from our own quest, which is the understanding of fine-tuning. The idea, though, is that one of the necessary conditions for the Big Bang to have the tiny seeds or ripples grow into stars and universes is the existence of dark matter. And without dark matter, and we never think of dark matter, we think that our matter is the real matter, but it turns out our matter is only a very small part of the universe. Without dark matter, the formation of stars and galaxies would have been impossible. What dark matter is, we have no idea. Why it was formed, we have no idea. But we do now understand that it is absolutely crucial to life in the universe and is indeed part of the set of initial conditions that would lead to a life-giving or life-forming Big Bang. And so the most recent estimates of the contents of the universe are here on this slide, that 13.7 billion years ago, it's estimated that dark matter was 63%, neutrinos about 10%, photons 15%, atoms 12% of the universe. Today, as the universe has evolved, dark matter is 23%, all ordinary matter is about 4.6%, and dark energy, this mysterious substance hypothesized to make the universe expanding at an accelerating rate, a recent discovery in the late 90s, is about 72%. So why these things exist, it is unknown, but they are critical to our existence. And John Gribben and Martin Rees, in their book Cosmic Coincidences, say flat out that dark matter is critical to our existence. It helps control the exquisitely balanced expansion rate. And not only that, but it helps the tiny ripples of density difference become stars and planets. And so they say, and yet, without the dark matter, the invisible stuff of the universe itself would be a very different place and we would not exist. Does the dark stuff exist in a sense for our benefit? Well, we as Muslims certainly think so, that this was not haphazard, that this creation is very deliberate and that this fine-tuning is a testament to the idea that the universe is specifically created and purposefully created, because we see that if any of a very large number of things were just the smallest bit off, one followed by millions or billions of zeros, to that level of precision, life could not exist. And let us end this lecture by just reflecting on verse 8 from Surah Ar-Rum, Surah 30, because I have often reflected on this verse. And of course, God knows best its true meaning, but the Quran is saying, أَوَلَمْ يَتَفَكَّرُوا فِي أَنفُسِهِمْ مَا خَلَقَ اللَّهُ السَّمَاوَاتِ وَالْأَرْضَ وَمَا بَيْنَهُمَا إِلَّا بِالْحَقِّ وَأَجَلٍ مُّسَمًّى وَإِنَّ كَثِيرًا مِّنَ النَّاسِ بِلِقَاءِ رَبِّهِمْ لَكَافِرُونَ. Do they not reflect in their own minds, not but with truth? And here I interpret with truth as this amazing precision and this amazing fine-tuning. And for a term appointed, did Allah create the heavens and the earth and all that is between them. وَمَا بَيْنَهُمَا, here underlined. Yet there are truly many among men who deny the meeting with their Lord. And my focus here is وَمَا بَيْنَهُمَا, the heavens and the earth and what is between them. And when I was younger and I would read this verse, I never paused to think, what is between them? The heavens, we look, we see the stars, we see interstellar clouds, we know there are galaxies, we know there are galaxy clusters, and the earth and what it contains, but what is between them? And it's very interesting, and again takes us a bit afield, but if you're interested, go back to classical tafsirs, to Ibn Kathir, to Az-Zamakhshari, etc., and see how this was interpreted. Of course, without knowing about this notion of dark matter and dark energy, how could classical scholars, God bless them for their efforts, make such a link? They thought that what is between the earth and the heavens are things like people, animals, trees. Why? Because we're on the surface of the earth, mountains. We're on the surface of the earth, so we're above the earth, but we're below the heavens. I personally have now come to think, and God knows best, that what is between them is all of this mysterious stuff that we are now calling dark matter, dark energy. What is visible to us are some of the contents of the heavens, the contents of the earth, but what is between them is this pervasive material of dark matter and dark energy that is woven into the fabric of the universe, and as of now, almost entirely mysterious to us in its identity. Once again, I'm not saying this is what the Quran means, but at least it is something that we can think about. It is a possibility, and hopefully on the Day of Judgment, we will be counted among those who thought about the Quran, who reflected on the Quran. And inshallah, God will accept this prayer from us. I hope you enjoyed this lecture. Assalamu alaikum. Take care and God bless. And we will have still more to say, believe it or not, about the amazing fine-tuning of the initial conditions of the Big Bang. Once we get through that, then we will see many more examples of fine-tuning about the laws of nature, about the constants of nature, the fundamental constants that we talked about. And so please join us for the entire series of lectures. Assalamu alaikum and God bless.